I can share. Looks like everything is good. Thank you.
Yeah.
Yeah,
Yeah,
and this guy is
I was walking by here anyway, so I just figured I'd stop in and
yeah,
you know,
it was.
easier that way.
It's a mess today. It's just the last.
Oh yeah. It's
Yeah.
busy.
It's crazy.
Yeah.
I'm losing my mind.
Oh no.
So, how would that work? Oh, it's not. Gosh. Thank you.
Yeah. Yeah, no problem.
I guess
Cool.
I'm just gonna go ahead and start.
The
Yeah,
recording works.
recording works. Everything works. Yeah, appreciate it, Devin.
Yeah, if you need anything from me, let me know.
I will. I will. Yeah, thank you. And good luck.
Yeah, thank you. See y'all.
See.
Yeah.
Okay, so I guess I'm here. I'm ready. I'm very sorry. You know what? I went home to take care of the dog. I need to walk to because my wife is working, and I just needed to go and take him out for a potty break. Yeah, and then I was stuck in traffic driving all the way back. So because I was in a meeting from 4 to 5, and it was this meeting about we meet every month for aerospace ecosystem in Hillsborough County, and what's that other county south of Hillsborough that we have Sarasota? Yeah, yeah. So yeah, so there was that meeting. It went all the way to 5. By the time that I was in my car driving home, it was 5:15, and then when I got there, it was like 5:45. He was not cooperating. It took him a long time to come back home again. So it was just, and then every traffic light was red. So of course, yeah, yeah, of course. So okay, so what I plan to do is I want to obviously work on that sample exam that I posted, but in addition to that, let me just ask people online. Can someone confirm if you can hear me and you can hear me well?
Yes, I can hear
No,
you very well.
good, wonderful. So uh, before before working on the exam problem, and I'm recording. I'm not. I think I am. Yeah, I think I am recording. I'm sure I am.
I see
Yes,
it on
yes,
my
I am.
on
Yeah,
my screen. I see the
yeah.
symbol.
Thank you, Eric. So, okay. So first of all, I'm going to stay as long as you need me tonight. Okay. If you have more questions, I'm not going to cut out at 7 and run. I'm going to stay as long as you need, so you can ask all of your questions. So that's that. Just to give you this peace of mind. So. Um, Okay, one thing that I want to do before getting to those problems, exam problems, you know, sample exam problems, I want to work on this one for you. Uh, this is a problem associated with losses, friction losses, and I think working on this is going to prepare you a bit better. So you see the problem statement there. It says we have a pump that's delivering 0.6 horsepower to water at 68 degrees Fahrenheit, flowing in a 6-inch diameter asphalted cast iron horizontal pipe at 7 feet per second. What is the proper pipe length to match these conditions? So problem wants us to find pipe lengths. Okay, so velocity is given. Obviously, we know what the material used to build the pipe is, so we have the epsilon. We have the d, so we have epsilon over d. We have d, we know it is water, so we have water's properties, and I will provide all those properties to you. I will also provide you whatever conversion coefficient you might need. So for example, if you need to convert that 0.6 horsepower to basic units, I will provide you with that if I give you a problem in British units or whatever in the exam. So I will provide you with conversions. So okay, so we have d diameter, we have velocity, we have obviously rho and mu for water. With that, we can go ahead and calculate Reynolds number, right? And then we know what the pipe is built of, so we can go ahead and calculate epsilon over d. With those two, we can find friction factor. And when we have friction factor, we can find HF, which is FL over dV squared over 2G. And when you have HF, it's like you have, well, you don't have L actually, and that's very, but then you have pump's head, which is 0.6 horsepower. Pump head is going to be equal to friction head. You make that assumption. So you pick the pump because it's horizontal, right? So the pump doesn't need to do any work to elevate water. It's just the pump is there to basically overcome whatever friction losses that we might have there. So that's how we know what HF is. And then from there, we can calculate L. Okay, so let me start writing down what we have. So, okay, so the first thing I'm going to do then, I'm going to write down P power is equal to M dot G and then head of the pump. So then from here, we know that head of the pump is going to be power, which is given to us, divided by M dot G, or power divided by, what is M dot? M dot is rho VA, right? So rho VA, and then multiplied by G. So, well, I'm going to plug in all the values that we have. So head of the pump would be its 0.6 horsepower, but then we need to convert this horsepower to foot pound force divided by second. So every horsepower is equal to 550. It's 550 pound force times foot divided by second. You know, Newton meter is joules, right? It's force times displacement is work. So now instead of Newton, you have pound force, and instead of meter, you have foot. So that's joules. Joules divided by second is watt. So that's why that pound force times foot over second is basically power. Okay. So, but that every 550 pound force foot per second is equal to 1 horsepower. So if I multiply 0.6 horsepower by that 550, then I've basically converted my power to pound force foot over second. So that's the power, and then the whole thing, the whole power is divided by rho VA times G. Okay, so well, rho times G is equal to gamma, right? So then instead of VAG, we could basically say V area gamma. Okay, and then gamma for water is 62.4 pound force over foot cubed. So that is basically your gamma. So gamma then is 62.4. And then that multiplied by V, velocity is 6 foot per second. So that's 6 foot per second. And that times area. And what's the area? We are dealing with a circle. And that 6-inch that we have is the diameter. So it's pi over 4 d squared. But that needs to be converted to foot. So it's pi over 4, 6 over 12 squared. This is going to give you, and you go ahead and simplify this whole thing, and then that is going to be in foot, obviously, squared, right? So what happens here is, look, you have a foot squared times foot, which is going to cancel out this cubic foot that we have there. So then we're left with pound force over second, right? And that pound force over second, let me go to a different color here so you can tell what is being canceled by what. This pound force over second is going to be canceled by this pound force over second. And all is left for us is that foot. So that's how we can basically confirm that with what we did is correct, and we are basically finding head of the pump, which is supposed to be in either meter or foot. So then head of the pump ends up being, I've already done the math here for you, that is 4.48. 4.48. So that is head of the pump. Now, The tricky part here is that we're going to, as I said, as I explained earlier, we're going to make this assumption that HF, or friction loss, is equal to head of the pump. You use a pump to overcome a couple of things. One of them is HF. The other thing would be that elevation. Alexa, what? Oh,
Yeah.
So,
Thank you.
so sure. The other thing is the elevation. If the pot was actually, if the pot was going up or if the pump was going down at a certain slope, right? Then we needed to have that delta Z. Well, in this case, it's horizontal, so we don't have to worry about that. So we say H of the basically losses is going to be equal to head of the pump is going to be 4.48, and that is equal to F L over D squared over 2G. Okay, and let's don't forget you're looking for L. The problem wants us to find the links. So in this thing, we know what D is. It's 6 inches. We convert that. It's 0.5. Basically, we know what is G. In British units, 32.17. We know what velocity is. That is 6. The only two things that we don't know there, one is F, the other one is L. But we know how to find F. So let's go after finding F first, and then we will plug everything in here, and we will find out L. So I'm going to go to the next slide and find F there. So how do we do that? We need to have the Reynolds number, right? So Reynolds number is equal to rho V D over viscosity, right? So now what is that? Well, or we can write it as VD over viscosity, dynamic viscosity over rho. So you see the rho is always there. It can't get combined into mu, right? And that is nu. So, or kinematic viscosity. So you can go as VD over nu. V, we know what that is. That is 6. D is 0.5 after converting that 6 inches to fluid. And then we have nu of water. Again, all these properties will be given to you either in a table or directly in the problem statement. Obviously, I don't expect you to memorize these. So now let's look at the units. So if you look at the units, we on the top, we have velocity 6, that is foot per second, right? That 0.5 is also foot. And what's the unit of kinematic viscosity? That's either meters squared per second or foot squared per second. So that is foot squared per second. It's always a good practice to keep track of units so you know you're not messing up anywhere. So you can tell that it's foot squared per second on the top, foot squared per second on the bottom. So this is a unit less. And the value, if you calculate that, is 278,500. And obviously it is unitless. So that's your Reynolds number. And then you can also find your epsilon over D. Well, how do we find epsilon over D? We know what material is used to build this pipe. We go to the table and we read the value of epsilon. So what's the material? It's cast iron asphalt. Let's go back to that table that I provided to you. So it's this, right? The same thing that we had in the other problem. So, and if we are, since we are going with food, it's 0004. So 0004, and that is in food, obviously. So what is D? A common mistake generally when you're working on this problem in the heat of the moment, you just forget converting these units. We can easily go ahead and divide that by 6, and then you end up with a completely different value, right? When you go to Moody chart to read the value of F. So you have to be very careful. You don't divide this by 6, you divide that by 0.5 in foot because 6 is in inches, needs to be converted. So it's 0.0008 then, right? And that is unitless. So using epsilon over D, we have its value and Reynolds number. We go to Moody diagram. And then from there, we read the value of F. I'm going to practice that now video and see what F we can read there. So 278,500. And you know that 278,500, you're not going to be able to spot that like precisely on that diagram because of the resolution that it has. And epsilon over D is 0008. Let's go and find that diagram somewhere. Yeah, here. 0008 is this. It's good to actually have an epsilon over D that has a line there. Otherwise, you have to read between the lines. So that's your 0008 line. Let me mark that so I'm not going to lose this line there. Now, what is my Reynolds number? It was 278,500. So see, this over here is 100,000. So this line over there is 200,000, right? I'm 200,000, 280,000 basically, 278,500, 280. So I have to be close to this line, which is 300,000, right? That is 300,000, but a little bit before this 300,000. I'm just gonna go up somewhere here and see at what point I'm going to cut through that line there. So you see, that's the line. I'm just going to read it there. And it really doesn't matter if you move to the left or to the right, the slope of that curve is just so small. It's not a sharp curve that if you move to the left or right a little bit, it's just going to jump up or down. It's pretty much a horizontal line, especially when you go to larger Reynolds numbers, right? So see, if you are at very small Reynolds numbers, it's very sharp in the beginning of the curves. But when you're at large Reynolds numbers, it's pretty horizontal. So this line over here, let's just see what that is. It's this line. So this is kind of like 0.02. So I'm going to go with F 0.02. 0.02. And now I'm going to go back to the previous slide and plug everything in there and find the value of L, which was the length of the pi. I brought this problem to you because one of you asked me, is it always like that we are after HF? So this is an example that you're not really after HF. You do the very same thing, but you're finding another variable in your equation. So this is 0.02. D is going to be 0.5. G is going to be 32.17. V is 6. Let me redo that. So, and then from here, you can go ahead and find the value of L. So the value of L is going to be roughly, let me see. So I would say then L is that 4.48 times 0.5 times 32.17 divided by 0.02. And then, oh, and there's a 2 there. Sorry, I forgot 2 before. It's 2G. So there's a 2 before that 32.17. So it's times 2 times 32.17 divided by F, which is 0.02, and then 6 squared. So from here, you can find the value of F. Does that make sense, what I did here? You know how this can be very complicated, and I'm not going to give you a problem like that because you won't have time to deal with it. It can be very complicated if D is unknown. I could have given you the value of L. I can give you the very same problem. And I'm not, let's say we don't change anything here. So this is going to be roughly 203, 203 foot. That's the links. Let's say I give you the links. I take D out. And again, I'm not going to give you that. I'm like, what is D? And I give you the links. And I tell you that that links is 203 in the problem statement. Now you're in trouble. You know why? Because you can't even find Reynolds number. You don't have D. You see how changing one thing can make this very difficult for you. You don't know what Reynolds number is. If you don't know what Reynolds number is, you not only you don't know what Reynolds number is, you don't even know what epsilon over D is because you don't have D. So you can't use Moody chart. You see, I'm bringing it up to your attention. I'm not giving you a problem like that. We ran out of time, right? But in an ordinary semester, I would do that. I would actually give you examples. We would work those examples in the class. You know what you have to do there? How you deal with a problem like that? You guess a solution. You guess a solution, and you guess a value for F, for example. You guess a value for D. You guess a value for. You go through it, and then you have to reiterate. You know, it's kind of like, remember that technique that we have in math? If we are solving an equation, what you can, we are solving an equation for X, for example, and we don't know how. So you keep one X on one side, you move everything else to the right side, and then you guess a value for X. You put that on the right side and you solve it, and then you get a new value for X. And then now you put that new value for X in there. So you have to do something like that if you ever encounter a problem like that. So for example, let's say I ask you to solve this X minus X raised to 5 minus 4X squared minus plus X, for example, minus 3 equal to 0. So how are you going to find that? Do you have a way of solving that other than draw? If let's say you can't plot that. Well, if you don't have any of those things, so what would you do? So what I'm saying is that you keep that X on the left side, you move everything to the right. If you move everything to the right, you end up getting this, right? And now guess a value for X. X would be 2, for example. Okay. And then you know what? I'm going to calculate X accordingly. It's that 2 raised to 2, 2, 5 plus 3, and then find a new value for X. And then plug that whatever you find there back in here again, and then find a new value and go over and over and over until it diverges. Sometimes until it converges. Sometimes it does not converge. It actually starts diverging. And then what you have to do is you have to go back to your equation and find another way to define X. So for example, what you do is you say 4X squared is going to be equal to X raised. I'm going to take a question, Eric, in a second. So 4X squared, and then you keep the other things, X raised to the 5 plus X minus 3, divide both sides by a 4, and then take a square root of. You see, that's another way of defining. Then try this. Do the same thing. That's the iterative technique. If D was unknown, you would have to follow this logic. You would have to guess a value for F, go over that loop until it converges. Good news is, the reason that I'm telling this, I'm sharing this with you, is that there is a good chance that you will have to deal with a problem like that if you decide to, go into, let's say, HVAC or piping, designing pipe systems business. So then, yeah, that's how you deal with it. Okay. Anyway, but I'm not going to give you a problem like that. If that, yeah, you don't have to worry about this for Thursday. Okay. So with that, Eric, please go ahead and ask your question.
So you were referring specifically, that is, to guess and check?
I'm referring specifically to what?
To guess and check when it, like, if D is missing, we have to like guess and check or something?
Yeah, you have to guess your solution, and then you go with whatever you guessed, you find D, and then you go ahead and you calculate Reynolds number with that D. You go ahead and now you find the value of F. Does that make sense? And you keep repeating this until it converges. But again, this will not be covered in the exam. I just want to bring it up to you and tell you that it could be complicated if F was unknown. Okay, you don't have to worry about that this Thursday. So with that, let's move on to, okay, let me ask you this. Any questions about this problem that we worked on and found F?
That kind of applies
Okay.
as well. So the tables that you that are supplied to us, there's kind of two for the 90-degree elbow, and one seems like a regression, like a calibrated kind of curve regression.
You're talking about these things, right?
There's another one. That one compared to like taking the 90-degree elbow of the table, where it tells you the diameter of the pipes. So which one would you use in each situation?
You know what? I would use the table as much as I can, unless you're dealing with a case where, for example, you see the diameter that you have for a screw is up to 4 inches in the table. And then the flange is up to 20 inches, so you have more data for the flange. But let's say it's the screw, and then the diameter that you have is 8 inches. Then you can't use this. Then go to that graph.
Okay.
You know what I mean? So use the table as much as you can. Now that we are at this, let me tell you something else, which actually what is something that happened in the problem that you're submitting tonight, homework assignment. The elbow was connected to a pipe that has a D of 3 inches. You see, and 3 inches is not even in this table. So what you need to do, you can do two things when you deal with a problem like that. Very first thing that you can do, you can interpolate. Okay, and I hope that's what you did. In this case, since 3 happens between 2, right in the middle of 2 and 4, interpolation is easy, or basically averaging it, averaging your values. I don't remember if it was a screw or flange. Do you all remember? Flange? Okay. So if it was flange, it was between 8.5 and 6. So you kind of average these two. Yeah. Another thing that you could do, and if you do that, that's also an acceptable practice, is you could go with 8.5, i.e. the value that's given for 2. And why is that? Because you want to be on the safe side. You're like, okay, so I know what's the value of K if it was 2 inches. I know what's the value of K if it was 4 inches. I'm 3 inches. I'm obviously going to pick the value that I have for 2 inches. So that you're on the safe side. That's an acceptable practice in engineering of pipelines and pipe systems. Okay. And that's a good thing to do because, and either way, I would accept either way. If you did averaging, if you do an interpolation, or if you go with the, if you want to be conservative with your design, that's also acceptable. It is going to, because over the time that you use your pipeline, the stuff that is in water is going to start building up on the inner walls of your pipeline, and the diameter of your pipeline is going to actually get smaller. And as it gets smaller, as you can tell, the value of K is larger for smaller values of diameter. Look at what you have at 1 inch, you have 13, and then at 20 inches, you have 5.5. So you have more losses when it's smaller. So it's okay then if you go, when your number happens between 2 and 4, for example, it's okay to go with 2. If your number happens between 1 and 2, it's okay to go with what you have for 1. It's also okay if you want to be precise and you do an interpolation. But it's always recommended that, again, in engineering practice, at the end, you need to, for example, if you're finding an HF, and then according to that, based on that, you're finding your head for the pump, go with a safety factor and then add something to it, 20%, 30%. As long as you know what you're doing, as long as you're reporting what you're doing to your customer, you're telling them that this is the precise, but if you want to be, you know, sure that your system is going to basically perform as well in the next 10 years, let's just, you know, go with a pump that's 20%, 30%, 50% more powerful. Okay. So since you asked, it kind of reminded me of that too.
No, that's a big 20. K values are so close that, like, if you have a value between those two, you can just go with the 8 value.
Yeah, yeah. And you see why it's happening there. That's also a very good observation. You see between 8 and 20, the values are not changing as much. It's because it's already so large that all those losses, it's just like some sort of saturation is happening with respect to diameter, right? So it's just so large, the diameter, when it's 8 and beyond, that the impact is already very small. Any other questions? Okay. So with that, let's go and look at the first problem that I gave you in that sample exam. So one thing about the sample exam that someone brought up this morning was that, will the exam cover only the stuff that we have in this sample exam? Well, obviously the answer is no. It's just a sample. This is just a sample exam to tell you how complex the exam is going to be, right? And also to show you that it's just going to be, again, as I've said many times, it's not going to be anything outside the, how can I get rid of this thing? Okay. I think now if I go back to this mode, hopefully you won't have it there. Okay. So back again. This? Oh, this thing over there. See? Oh, yes. Thank you. Thank you. Oh, and it actually disappears too. So, okay. So it says, write the general form of the continuity equation, and then it wants us to simplify under the given conditions. It says incompressible in this case. Well, what is the continuity equation? This is a problem from chapter 4, section 4. Well, you always write the general form when they ask you to write the general form. And then when you're simplifying, simplify only for those given conditions. Don't write steady and then simplify for steady. Read the problems, because this happened in the other exam 2 and problem 1. So in problem 1 of exam 2, for example, I asked you to simplify for having 1D inlets and outlets with uniform flow. I did not ask you to simplify for incompressible or simplify for steady, right? But then many students had done that. They actually simplified for other conditions. So read the problem statement very carefully and simplify for the given conditions. So, well, what is the continuity equation? It's change of rho with time, right? Plus rho u with respect to x, right? Mm-hmm. Correct. Correct. And then when it says simplified is for incompressible conditions, then what happens when it's incompressible? Yes. The first, basically, when it's incompressible, what happens to rho? Rho becomes constant, right? When rho is constant, then it would not change with time. Then you can set that equal to 0. If I had set simplify for steady conditions, that's all you can do. You have to leave it like that. You don't assume that rho is constant. Because it can be compressible steady. Okay, so if it was a steady, if we were simplifying for a steady condition, we would leave it like this. We wouldn't simplify any further, right? Because a steady means rho is not a function of time, but it can still be a function of space. Now, in this case, it says it's incompressible. So it means that rho is constant. When rho is constant, it's constant with respect to both time and space. So that first term is then equal to 0. And then you can pull it out of the next 3 terms. And then when you pull it out of the next 3 terms, you end up getting this. And now you can divide all 3 terms by a rho, everything by a rho. Basically, what happens is that rho cancels out. Okay. And the first equation, which is the general form of continuity in XYZ coordinate, I want you to pay attention to the units. So the units of those terms must be equal, right? You can't sum up things that are of different units. So the unit of the first term, which is d rho dt, has to be the same as the unit of the second term, which is d rho u dx. Is that correct? Can you see that the units are the same? What's the unit of the first term? The unit of the first term would be kilogram per meter cubed, which is unit of rho, and then you divide that by unit of t, which is second. What's the unit of the next one? You have kilogram per meter cubed times velocity, which is meter per second, divided by meter. You see that meter cancels this meter out, and then again, you end up getting kilogram per meter cubed per second. Why am I bringing this up? Because if in the exam you're writing the equation and then you are doubting that if this is the correct version of the equation that you wrote down, that's how you can tell. If the units of terms that are being summed up are not the same, it means that the equation that you wrote down is not correct. Okay, that's one way of checking your equations if you're doubting it. So, any questions about this? Is there any question online about this?
I have a question. Well, because you just brought up that there is steady, that you could have steady compressible flow. Like, what does that mean? Like, as opposed to incompressible safe flow? Like, what's the difference?
Steady compressible versus incompressible, right?
Yeah.
Well, when it's incompressible, it means that rho is constant with respect to time and with respect to space.
Yeah.
But when it's steady, but it's compressible, it means that rho is constant with respect to time, but is not constant with respect to space.
So essentially, you could have steady flow, but density changing in space.
Yes,
It's possible.
yes, correct. And then your equation would end up looking like this. After you simplify it, the equation ends up look like this. So you don't basically, you can't pull out rho because rho might change with respect to space. You see what I'm saying? You have to leave it like this if it was just steady. If you
Yeah.
tell me that flow is steady, that's how I simplify the equation to. I'm not going to be able to pull rho out because it's steady means no change with time. It doesn't mean no change with the space. So I have to leave rho in there. Does that make sense?
Yes. So
Okay,
yeah.
good. So let's go
I
and look
think.
at the next example that we have. That's the one that I talked about in the class today. So it says we have paint guns are used to spray paint on solid surfaces. The average diameter of droplets created by the gun, which is D, basically depends on, says D depends on, I'm just listing every variable that's important. See, yeah, depends on initial shear stress, which is tau, not paint viscosity, mu, paint density, rho, liquid pressure at the spray nozzle's outlet, that's P pressure. And then it says the surface tension of the paint, which is shown as, what is that thing, sigma? Yeah, sigma and Newton per meter, that's surface tension, right? And then volume flow rate, which is Q, and then nozzle's outlet diameter, which I'm showing it by lowercase d. How many dimensionless variables do we need to describe this? How many dimensionless variables do we need? Is it 7? I'm counting 8. It's 8 minus 3, 5. Okay, because it says the droplet's diameter is that capital P. And then the last D is the outlet diameter of the nozzle surface, of the nozzle's outlet. Does that make sense? So you have 2 different diameters here. So it says the droplet's dimensions or diameter depends on these things. So you have to count that first thing, which is the droplet's diameter. Does that make sense? So you have 8 things here. So it goes 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now he said, what is that? So, so what is that? That is surface tension. It's like, what is surface tension? I've never heard of surface tension. Do we need to know these variables when you're working with them in the pi theory? No, whatever. As long as you know what's the unit. And that's why I gave you the unit, because you don't know what unit of surface tension is because you've never worked with it, right? But if you have the unit and you know the unit is Newton per meter, you know what Newton is. It's kilogram times meter per second squared, right? Mass times acceleration. And it's being divided by another meter. So you can find the unit of, as long as you have the units of something, you know what its dimensions are. So, for example, you know what's the unit of, the sigma. Unit of sigma is Newton per meter, and Newton, as we just said, it's kilogram meter second squared divided by meter. So that thing is kilogram per second squared. So what's the dimension of sigma then? Then sigma would be mt raised to negative 2. So you don't know what sigma is as long as you know what its dimension is. And now you're going to treat it like every other variable that you deal with when you're applying the pi theory.
Just for on the exam, like actually in it, like just as a suggestion, is there any chance if like surface tension or something like that is on there, we could use like gamma or something? Because like I was kind of confused on this question because I thought that when I saw surface tension initially, I saw omega and I thought back to like MOS to where omega is usually newtons over meter squared. So I like couldn't figure out if it was like a typo or if it was like that was supposed to be the units of it.
It's sigma.
Or sigma.
This is sigma, this is not omega.
Yeah, excuse me. I meant to say sigma. So sigma was used in MOS for force over area. So the units,
tension.
The units of that is
Normal tension. Yeah.
So I thought that
it's that. No, it's not that. You know how you should know that it's not that? Because it says this is surface tension, the problem sigma. Sigma in that course is normal stress, right? It's not surface tension. So that's how you know.
I guess I just
You just need to be patient with the problem statement and read it very carefully. You know what I mean? I get what you're saying. I get that this, because you've seen sigma before with a unit that's kind of similar to the unit that we have here, with a slightly different Newton per meter squared. This is Newton per meter. So I get it's very normal, very natural that it takes you there. But then you have to be able to tell that this problem statement says this is surface tension, and what you had there was not surface tension. That was normal stress.
I guess it was more of like not having the familiarity with the units of surface tension than having the familiarity.
But you have, yes, but you have to trust the problem statement. So the problem statement tells that this is sigma, and this is surface tension. Its unit is normal per Newton per meter. Just go with that Newton per meter. You know, if you go with that Newton per meter, you're gonna be fine. Basically, point, and that was the point of this, to tell you that you don't even need to know all of these variables that you deal with when you're applying the pi theorem. Okay, as long as you know what the unit is, or as long as you know what the dimension of the thing that you deal with is, you just treat it like every other thing. Just plug it in that thing, in that pi equal to, for example, sigma raised to a, and then your three repeating variables raised to b, c, and d, respectively.
Does it matter which diameter you use as a repeating variable, the inner one or the average one?
It doesn't. It does not, because they're both of the same dimensions. Okay. Someone was asking me this question. I had a conversation with one of your friends after the lecture today, and a very good point was brought up in that conversation. I want to share that with everyone. If when you're choosing your repeating variables, so for example, in the class today, I told you that you can't choose your repeating variables in a way that it won't work, right? I said, well, you don't have one unique set of repeating variables. Generally, you have more than one set of repeating variables that would work. But again, once we have more than one set of answers for repeating variables, there can be a set of repeating variables that is not going to work. So what would be an example of that? Let's say that, and that could actually happen when you have too many variables. That can actually happen. If you choose your repeating variables in a way that one of the dimensions is absent in them. So for example, let's say you have two diameters here, and they both are of the dimension of L. And you go ahead and you're like, okay, I'm just going to go and choose these two as two of my repeating variables. And then you choose something that doesn't have time in it. So for example, you go with density, which is just M over L squared, right? So now in your three repeating variables, you don't have T, you don't have time, right? So how would you expect time to cancel out then? You see what I'm saying? You have to have all, basically, when you're finding your pi's, you're grouping one non-repeating with three repeatings, right? You can't have either T or M or L in only one of these four variables, because then it won't cancel out. You see what I'm saying? So that's another thing that you need to consider when you're choosing your repeating variables. So if I go, again, in this case, if I go with, for example, the two Ds and then row, and then when I'm grouping these three, the two Ds and the row with anything else here, so for example, with Q, in Q, I have time. It's L cubed over T. That T is going to stay there because there is no T in any other variable to cancel this T. You see what I'm saying? So that's how you have to think about it. Okay. So, and then you ask me here, which D we would use. It doesn't matter because they are both of the same dimensions. But what is obvious here is one of your pi's is going to be the ratio of these two D's, right? Kind of like the problem that you had in homework assignment that you had I think D, which was the diameter of the propeller of your turbo machine. And then you had the change in head. They're both in meters. They're both length dimension only. One of the pi's that you ended up finding was that delta H over D or D over delta H, right? Same thing is going to happen here. Okay. So there's a question online. Please go ahead. Okay. I think. So
which of these variables is surface tension?
is that sigma?
Mm-hmm.
Yeah.
And then which variables did you say like
Look,
would not
let me show
necessarily
you
work as
something.
repeating?
Let me answer your first question first. It says the surface tension. I'm just highlighting the problem statement of the paint, which is shown as sigma in Newton per meter. Does that make sense? So sigma in Newton per meter is surface tension.
Mm-hmm.
Okay, what was the next question? What was your next question?
I'm trying to think which variables did you say would which kind of variables did you say like would not be ones that you should probably use for repeating variables?
Yeah. So what I said was, for example, I said if you choose this diameter and then this diameter, and then you go ahead and choose, for example, density as your repeating variables. Let me go back. Density as your repeating variables. I said it's not going to work if you do that. And the reason is you don't have time in each of these three. And therefore, when you're grouping these three with any other variable, you don't have time to cancel out time that appears in every other variable.
Yeah, so if
Does that make sense?
Yeah, so if you're working with three repeating variables, at least one has to contain time.
Yes, time, and one has to contain length and one has to contain mass.
So
Right?
it has to, yeah, so each set has to contain at least one of each of those like types of dimensions.
Yes. Yeah. So then when you're mixing these two repeating with a non-repeating, no matter what's in that non-repeating, you can go ahead and cancel everything out. Okay. So now with that, let's do it. So the problem statement says, use density, diameter, and flow rate here as repeating variables. So I'm going to go ahead and do, for example, that tau naught as my non-repeating, just to practice this some more. So, for example, my pi 1, let me change the color of this screen to, yeah, something that you can see better. So pi 1 is tau naught, for example, raised to a, and then I'm going to go ahead and have the three repeating variables. So, for example, rho raised to b, and then I said go with d diameter raised to c, and then what was the other thing? Q raised to d. Okay, so now what do? We plug in their dimensions. But what's the dimension of tau naught? How would you tell that? What's the unit of it? Newton per meter squared. So tau is a stress, and the unit of a stress is Newton per meter squared. And then we all know that Newton is kilogram meter per second squared, that divided by meter squared. So then this ends up being kilogram meter second squared. Yes, sir.
So I have a question. It's kind of like talking with somebody about this earlier today.
Mhm.
So tau's units are newtons per meter squared, right? And then we also have pressure, which
Mhm.
are also newtons per meter squared. So
Mhm.
does that mean that the pi equations we get for both of those are going to be the same because they're the same units? And the other three things we're treating as constants?
Yes.
Okay.
That is correct. And then actually we'll end up getting another pi, which is P divided by tau naught.
Should we do?
No, no,
Okay.
no. As long as you explain, you do for one of them, you do it for tau naught, for example. He's asking an excellent question. He's saying that unit of pressure is also Newton per meter squared. It's just like unit of tau, right? So then the very same thing that you're finding for tau, the very same pi one that you're finding for tau, if you want to go after pi 2 and now this time want to do it with pressure, because pressure is among the variables, it's that variable number 5, you can just copy paste what you had for tau naught, just replace tau naught with pressure.
Exam, would it be good to just do both of them just to like verify your answer?
No, I don't recommend that. You don't have time for that. If you want to verify, you know what you do? Plug in the units.
Gotcha.
Make sure all the units cancel out. If the units cancel out, you know that thing is correct, and then you can go ahead and do it. Right now, let me ask you this. So let me ask you. Can you guess what this part one is? If you had paid attention today in today's lecture, I gave you a few quick hints that you could actually use. What? But can you tell me how it looks like? Can someone without doing it look at this and write down what this pi is going to be like? I can do that based on what I told you today. Remember, I told you that a few things have the same unit. What was the thing that had units of pressure? And I used Bernoulli equation to show you that.
I remember it happened. I don't remember what it is.
I just did it, but it's, do you want to say it?
Yeah.
It's mu d over q.
Mu over OQ. Okay, let me write that down. Mu, what? Say it again. But we don't have mu here. It's tau. You're reading another one.
Oh, you're right.
Yeah. Do you have the tau?
Tau d the fourth over q squared.
Tau d over what? Rho q squared. Okay, so she says that. Okay. Yeah, okay, makes sense. Makes sense. So let me ask you this question. Think about Bernoulli equation. Okay. What are two terms in Bernoulli equation other than z? No, what are the two terms? The first, it's p divided by p over rho g. What was the other thing? P squared over 2g. Okay, so these are two terms in Bernoulli equation, right? What are the units of these? So the two have the same units, right? So the units of that p, let me fix my p there. P, okay. So these have the same unit, right? These two terms have the same unit. If I multiply them by a g, then that g goes away, right? So then what do we have there? Is it safe to say p over rho has the same unit of v squared over 2? Is that 2 doing something there? No, so I'm going to get rid of that. So is p over rho the same unit of v squared? So then can I say p has the same unit of rho v squared then? I'm just moving that rho there, right? Didn't you just say tau has the same unit of p? So then tau has the same unit of rho v squared. See what's happening here? And then what is v? Isn't v q over a? And isn't a d squared? See what's that? That's why you have d raised to the 4, because it's q over d squared is v, but then you have v squared here. It's rho v squared. So it's d squared squared d to the 4. Does that make sense what's happening here? So basically what you can say is that if you know pressure has the same units of rho v squared, then you know that you basically know that p over rho v squared is unitless. And you just said p has the same unit of tau. So then basically tau naught over rho v squared is unitless. And we also know then from here, I know that tau naught over rho q over D is squared. A squared is unitless because Q over A, and A is that D is squared, basically. I know there's a pi over 4 D is squared, but pi over 4 doesn't do anything. You're dealing with units, right? So that's how, see, that's what she found there, right? It's rho Q is squared on the bottom, and then you have D is squared, which is D raised to the 4, goes all the way up there. Does that make sense? What's that?
You did all that in your head? Like you just looked at it and you like.
Yes, yes. Yes. It's important for you to know that pressure has the same unit of rho V is. That's a very well-known fact in fluid systems. That unit of pressure is the same as unit of rho V squared. How do we know that? From Bernoulli, right? And then you also know that Q is a VA to all of these things. So now, with all of that, that I just wrote down, I'm going to erase this whole thing, and we're going to follow through the procedure, and we will see that it will end up there, right? Yes.
Exam, are you gonna give us the units, or like if we don't remember the units?
If it's something that you don't know, like what was that thing, surface tension, that you're gonna, wow, what is surface tension? Then of course I'm gonna give you the unit. But if it's density, you should know it.
Well, yeah.
What's the other thing that you struggle?
I forgot how.
Tau. Yeah. Is it fair to give units of tau? Yeah. What about mu? You need to know the unit of mu. Right? What's unit of mu?
Oh,
I'm sorry, I don't want to question. So, I had a professor that used to do that. He would be like, okay, any questions? And then when someone who would dare to ask a question, he would just go after them. He would ask them questions, left and right. And then, yeah. And then, you know what, midway through the semester, he was like, any questions? And he was just, good. That's what I want. So, so, okay. So yes, I agree with you. How might be something that you. I thought I'm going to be. I'm going to think about it twice before I. Yes. So, yeah. So let's go. So these are all I did here is just to tell you that you have so many different ways of saying what's going on, right? In terms of pies. So this pi analysis is very strong. Units are so strong. Units tell us a lot of things. So yeah, that's how a lot of scientists that have formulated formulas, they've done it just by paying attention to the units. Which is kind of like what happened in the problem that we worked this morning, that there was only one pi, and I said that's constant. So anyway, so let's do this just by following the procedure. So then we're going to plug in all the dimensions. Dimension of pi is 1. Dimension of tau, we found its unit, right? It's kilogram meter per second squared. It's on the right side of the board. So then tau would be m L raised to -1, T raised to -2, and then that's rho, which is M L raised to -3 raised to B, L raised to C. That would be L. What is going on? Oh, guys.
It's their way of us.
Yeah, they can't do that. So it's A plus B. You see what's happening here? We have this M, A plus B. Imagine if there was no M in the next 3 variables, right? If there was no M, obviously that M would never cancel out. So that's one. So, and then we have L raised to -A minus 3B and plus C plus D. Hopefully I'm doing it right. Let me double check. You see, that's also a step that you should always double check what you're very likely, that you might, very easy to make a mistake here. So it's L, let me double check that. C and then D and then T, we have T minus 2A minus 3D.
Isn't it L?
Oh, you see, that's right. Yeah, I did that on purpose.
Ah.
Let's see if he, because no one was paying attention. So yes, she is right. Oh, you see, then that messes everything. That messed up this for me because that L would be, yeah, yes, 3D, right? And then T would be what? T would be minus, oh, what's happening? Oh, okay. Only I can annotate.
Somebody else wants.
Oh, no, please. Please. Oh, don't do it. This is going to, yeah. So this laptop is already struggling. Please don't do that. So okay, let's double check again. Sorry. So I have L minus A minus 3B, and then I have C, and then 3D, yes, and then we have T minus 2A. What happened? You all changed my settings. Someone changed my settings there to, oh, Eric, did you do that?
No, I was only asking if it was your
2A.
band. If I did not do anything with your settings. I was only asking if your bandwidth was affected or something.
You can use there.
These, but that's just too thick. Okay, let me see. T minus 2A. Okay, I'm gonna live with it. I'm gonna live with it.
I did not change anything at all.
Okay,
I was only
okay,
asking
I
if
got you.
your bandwidth was affected or
Okay.
something.
Okay, we're good. We're good. Is this good? You're all good? Yeah. Okay. So let's write this down. Let's. What is it?
At the bottom, see annotate.
When you close out of it, it's all gonna disappear.
You're not writing on the actual PowerPoint, you're writing on the screen that's projected.
Oh, can someone come here and help me with this? Oh, I see. I got it. Is it good now? So I'm not. So how do I? It's still on that, I think. Oh, let me see. T. Yeah, it's still on this thing. Someone messed up the settings.
I think it was Evan John.
Yeah, someone requested to edit. Can someone help me here? Should I go ahead and here are my annotations? We are all annotations. Yeah. How do you close this? Well, we don't want to use that though. That's the thing. You know what? Let me.
What does the mouse one do?
Oh God. On the top.
That's right. Yeah, there you go. Right, go background. Right?
Oh yeah. Is this gone now? I think so. Yes. Okay. Sorry. This took forever. So minus D. Okay. I'm gonna wrap this up now quickly. So it's M. Okay. So then A plus B is equal to 0. And then minus A minus 3B plus C plus 3D is equal to 0. And then minus 2A minus D is equal to 0. So what do? We choose a value of 1 for A, for example, right? Let's say A is equal to 1, and then from there, B is equal to minus 1. Then over here, I have minus 2 minus D equal to 0. So D is equal to minus 2. And then let's find the last one. You're after what here? You're after, oh, okay. So please, guys, don't distract me, please. So what about, now we are after C. So we are after C. So this is minus 1 minus 3 times B, which is minus 1 plus C plus 3 times D, which is minus 2 equal to 0. So that would be -1 plus 3 plus c minus 6 equal to 0. And c would be c minus 4 is equal to 0. So c is equal to 4. You see, that's that 4 that we had, right? So let me highlight what we have for different variables. So a is 1, b is -1, d is -2, and c is 4. So then what we are going to find here is, for example, for this one, if I could just move this away. Yeah, you know what? Let me just leave the. I don't know how this happened. Where did that come from? This interacting, annotate. How can I just get? Okay, I think it's gone now. Yeah. So let me go back to presentation mode. And okay, so now I can write down what I have for pi 1. So pi 1 then is tau raised to a, which is going to be tau naught, rho raised to b, b is -1, and then we have d raised to c, which is d over 4, this whole thing divided by rho, and then, no, I'm not, I'm good. No, this is good. And then rho, and then we have q raised to d, and d is 2, so it's rho huge. You see, that is what we guessed by doing what we did early on, and that's exactly what you had you found. So you see, so now, so you said, sir, you said we could actually, what we could do is, now you're after p, the dimensionless variable for pressure. You don't have to repeat all of this, and you could actually, only thing that you need to do, you need to substitute that tau naught with pressure, and then you have pressure times d raised to 4 over rho q squared. So that's what you do. You don't have to repeat that whole thing. So you already have quickly your pi 2. Why do you do that? Because the unit of tau naught is the same as unit of p. So unit of P pressure is Pascal or Newton per meter squared, and then tau naught also has a unit of Newton per meter squared. So that the same thing that is going to make tau naught dimensionless is going to make P or pressure dimensionless. So then when you find it for tau naught, you already have it for pressure, right? And then your pi 3 would be, so basically you found 3 of them, because now let me go back, your pi 3 would be p over tau naught, because the two have the same units, right? And your pi 4 would be, for example, what? D over d. So we quickly found 4 of these dimensionless variables out of 5. Okay, now we only need to find the last one, and the last one is going to be based on, for example, you can do it for sigma. Okay, so just to give you ideas of how you could handle this quickly. Let's move on from this, because it would be just repeating the same thing in the same process. Yes.
So just a quick question, like just for clarification. So like when you're just solving it to describe the problem, it really doesn't matter like how you get to your dimensionless like variables as long as they cancel out to one in the end, correct?
Yes.
But when you're solving to actually try to like find something. So like for example, if you were like doing the coefficient of drag, would it matter more which ones you select them because you like would want to have like
Yes. Because there you have this physical understanding and you really know what you're looking for. It's the same thing here. You know what I mean? But here is a more complex and a broader problem. And if we wanted to get into those discussions, it would become very complicated. But when you're solving this problem, you know what really matters to you. And you really want to make those things dimensionless, which is what will kind of like dictate those repeating variables for you. You know what I mean? because things that matter to you and you want to deal with them as a non-repeating, you're not going to put them among repeating. So then they're going to appear everywhere. You want to isolate the thing that matters to you. You know what I'm saying? So then when you're reporting your values, you have this one pie that is associated with that thing. You see what I'm saying?
Yeah, makes sense.
Yes.
There's a little d given, we pretty much always assume there's a large D, because when I did initially, I missed that. Like a capital D, there's a little one, you just assume always. Okay, and then another question was, are you gonna probably give us the repeating variables in the exam because of the amount of time that we have,
Or unless it's just very similar to one of the problems that we've done before. You see what I'm saying? So for example, we worked on a pump problem within the lectures, right? And in that problem, I told you that go with rho and go with omega, rotational velocity, and also go with a density, right? So you already worked that problem. You've already seen that problem. And it was the same variables when we worked on the homework assignment, right? It was again rho, RPM, which is the same as rotational velocity, and then density. You know what I'm saying? If it's something that's like this, a new problem that you have not worked on before, yes, I'm going to tell you what those repeating variables are. Okay, yes.
You decided yet if this type of question is going to come with just finding pi, or is it also going to come with like applying numbers to it, like what we did with the cylinder in class?
I have not decided that. I have not decided that. I haven't written the exam yet. I did not want to do that because then I can't help myself but giving you hints that what the problems are going to be. So I don't want to write the exam before this. So, but I haven't decided that. But you should be able, look, there are a limited number of and type of problems that we've worked. Just, oh, and another thing that I told whoever stopped by the office today in the office hour, I know I said that I'm repeating myself because I think it's important. It's worth it. It's worth repeating. Do not read through the solutions and then assume that you know how to do it. Do it. Okay, because if you read through the solutions, it makes sense to you. You might think that you know how to do it, but then when you do it on your own, you're going to make a few mistakes here and there, and those few mistakes are enough to lose 5 to 10 points. And if there are 4 problems there and you use 5 to 10 points on every problem, that ends up being like 20 to 40 points. And then your grade ends up being somewhere between 60 to 80. You see what I'm saying? So a problem that has 30 points, if you make a small problem, a small mistake here and a small mistake there, you're going to lose 5 points there. And the next problem is 25 points. And you make some problems here, some mistakes here and there, and you lose another 5 points, 5 to 10 points. See what I'm saying? So there is no room to make these little mistakes. Don't think that it's okay if I make this mistake, if I make that mistake, you know. So you've seen my grading. I try to be as generous as I can, but then don't leave anything blank, because then there's nothing I can do for you when it's just blank or halfway through, you know. So do good time management. So because of that, you have a limited number of problems. You have, I don't know, maybe 20 to 30 problems, 20 maybe problems that we've worked. Go over those problems one more time. Okay. Don't try to expand that data set that you have on your own. Instead of working more problems, work the problems that you have a few more times. If you are thinking about what would be the best way to prepare for this. Okay. So yeah. So now what I can do is, let me look at the last problem. Okay, the last problem said use Navier-Stokes equation to formulate flow velocity for co-ed flow in the presence of pressure gradient in flow direction. Yes. Eric, do you have a question for me?
So what you were telling students, like what you were suggesting is that they, let's say, do the actual problem first and then look at the solutions to see where they made the mistakes, because you're saying if they just read it,
It's
then
okay
they
if you
might make
read
a
it
few of them.
once. If you want to learn, it's okay if you read it once, but don't stop there. Do it after you read it. You know what I mean? Do it without looking at my solutions, and make sure you can do it on your own. Okay. So let me explain this problem 4. Problem 4 is directly from the lecture notes, co-ed flow. Remember, have I defined quiet flow? It's the last problem that we worked on in section 4. So quiet flow is that problem that you have a fixed surface and then you have some fluid and then you have a plate on top of this fluid and then you move that plate with velocity v. That's what quiet flow was. Okay. Now, when we solve for quiet flow, we solve for quiet flow assuming that we have pressure gradient or we don't have pressure gradient. In this problem, it says solve for quiet flow in the presence of pressure gradient. Okay. So this is a problem directly from the lecture notes. So I'm going to go to that problem in the lecture notes and show it to you there, just in the interest of time and make things a little bit easier here for us. This way I can use time a bit more efficiently. So let me go there. Okay, so section 4. Okay, so okay, so this is the quiet flow that we worked on in the lecture notes. So that's also a very important problem. And you see that I'm asking about it here. So these assumptions that I made here are important. You need to write them down when you're working on that problem. So we are going to assume that you're dealing with a 2D problem. You're going to assume that rho is constant. You're going to assume that it's steady, so you can simplify your equation. You're going to assume that, well, first we assume we don't have pressure gradient, but in this problem it says in the presence of pressure gradient, right? So you're going to assume that dp dx is non-zero, which was the next problem that we worked on. It was here. So here I wanted you to analyze the quiet flow in the presence of pressure gradient in the x direction. So you see, that's what that problem is asking you to do. But what's very important here is have the simplified that equation on top that's written in red. So that's your conservation of momentum differential form of it in the x direction. And you see, I'm setting gravity in the x direction equal to 0. That's an assumption that you're going to make. Why? Because generally we don't have gravity in the x direction, right? Pressure gradient. Here I'm setting it equal to 0, but again, next slide, when I'm solving it in presence of pressure gradient, you keep that term. Then it says U, for example. Oh, that's a very important thing. We talked about U only changes. You see this thing over here, that discussion that I wrote down for you in the middle. I say U only changes with Y because by moving in the Y direction, we get closer to the wall. U doesn't change in X. U doesn't change in Z. U changes only with Y in this problem. Let me go back. You see, this is your Y axis, right? That's Y axis. If you move in that Y direction, by moving up or down, you're basically, by moving up or down, let me go to laser pointer. When you move up or down, you're changing your distance from the wall. And we know that the closer we are to a wall, the slower the fluid is going to flow, right? So that's why we only have du dy in this problem. You don't have du dx. You don't have du dz. See what I'm saying? So when you don't have du dx, then obviously you don't have, see, du dx is equal to 0, du dz is equal to 0. If du dx or the first derivative of u with x is 0, then obviously the second derivative of u with respect to x is going to be 0 too, right? Because you're taking derivative of 0. So that's how I'm setting this equal to 0. That's how I'm setting this other one equal to 0, because if du dz is 0, second derivative would also be 0. It's a steady, right? So then that term is equal to 0. This is 0 again. We just talked about it. We don't have du dx. That's 0 for two reasons. One, you're assuming that you're solving a two-dimensional flow, so you don't have velocity in the z direction. And two, you don't have du dz. So basically, both of these terms that are being multiplied into each other are 0. You don't have velocity in the y direction. When you have fluid between these two plates, and then here one of them is stationary, the other one is moving, all of that fluid that you have in between is going to start moving only in the x direction. So you just have u, you don't have any v. right? You don't have any W. And that's why over here on the right side, that term is equal to 0. Basically, in this case, where we did not have pressure gradient, we ended up only with one term, which was the second derivative of u with y was equal to 0. And all we needed to do here was we needed to basically integrate this once and then integrate it another time, so we get at u. And then we plugged in the two boundary conditions that we have. What were the boundary conditions? Velocity at the bottom wall is 0 because it's a stationary. Velocity at the top wall is equal to the velocity of the wall. You plug them in there and you find the two. So that's without pressure gradient. And then when I did it with pressure gradient, I kept that term there. Okay, and then when you were integrating, it just ended up being a second degree polynomial instead of a 1 degree polynomial that we have. Okay, so this is important, this example. The reason that I included that in this sample exam was to encourage you to go back and make sure that you read that example and you know how to deal with it. That's the only flow problem that I covered that was solved directly from Navier-Stokes equation. I give you only one problem, and that's this. So I expect you to know how to work this problem. Okay, so so that's problem 4. Any questions about this co-ed flow? Look online. Is there anything there that you would like me to explain about this co-ed flow? Yes, sir.
Specific like types of like flow cases we would need to know for the exam.
Like this.
Like, is there like a specific name for when like both plates are moving or anything like that, or no?
Yes, we can have a problem like that. I won't cover it. I won't cover it. But I want you to know everything about this. I want you to know everything about this co-ed flow. For example, if I ask you to, for co-ed flow, write down the simplifying assumptions that would lead to this solution. Like if I want to ask a question that's quicker about it, I don't want you to do everything from scratch. I want you to write down the assumptions. Or if I ask you that, why can I make this assumption? In this flow, I'm going to give you this problem example, for example, this problem statement, and tell you that why am I allowed to assume that the second derivative of u with x and the second derivative of u with z are 0? Explain that. See, I want you to be prepared. Yeah. Then how would you explain that? You're like, well, because velocity changes only when we move in the y direction, because when what I've written there, because when I move in the y direction, I get closer to the wall, or my distance from the wall changes. If you move in the x, your distance with the wall doesn't change. The wall is what's slowing the flow down, right? If you're at the same distance from the wall and you're just moving in parallel to the wall, your speed is not going to change. And when you move, let's see, look at this floor. You can move in parallel to the floor in this direction, that's x, or in this direction, that's your z. So you are still at the same distance from the wall. But the moment that you stop moving up or down, or you're moving in the y direction, that's when you start having velocity gradient. Okay, so I want you to know this case very well. Again, in an ordinary semester that we don't lose, like how many sessions did we lose? 4 sessions, right? So I give you examples like I used to, actually, at some point I dropped it. I used to give the example of having 2 cylinders, one inside another one, the outer cylinder stationary, the inner cylinder rotating. And then ask you to find the velocity of the flow, because the rotating cylinder would make all the air between the 2 cylinders to rotate. And I used to ask that question, and I used to work that within my lecture. So what I'm saying basically is this, something like this. I'm going to draw it quickly so you can get an idea. So one cylinder inside another one, let's say the outer one is a stationary. That's kind of like a rotational co-ed flow. And then the inner one rotates. So the water that, for example, you have in here is going to start rotating, right? And then velocity of water over here would be 0. Over there would be r omega. R being the radius of the inner cylinder and omega being its rotational velocity. I used to work this problem at the lectures. This semester, you skipped it. Again, it's just going to be about this co-ed flow. I expect you to know it. So whatever questions I ask about it, you should be able to answer. Yes.
Like the polar version of this equation.
Yeah. Yeah.
Because I was thinking, I can't really do that Cartesian.
No,
well.
it has to be cylindrical or polar. Yeah. Which we didn't get into the details of it. So the good thing was that everything was covered. We managed to cover everything that you needed to know. Sometimes I could not cover more complex problems of those concepts. That's what actually happened. Like, for example, and those are two things. There were two things that I could not get into the depth that I really wanted to. One, internal flows. I really wanted to solve a problem where D was unknown and you had to go through that iteration. That was one thing I could not cover. But I talked about it at least, and you know that that challenge is there. And the other thing is this. I couldn't cover more specific cases that you could solve for using the Navier-Stokes equations. Okay, so I don't want to keep you here any longer. I know there's one more problem in the sample exam that I did not solve for now. I will solve that and I will post the solution to it. I'm going to let you ask me whatever questions you have. And if you don't have any questions, you want to go, feel free, you know, and but I'm gonna be here. And if you have any questions, just let me know. And thank you for coming here tonight and for waiting for me when I was late. Yeah. To well, I'll post the slides that I'm going to update everything. I'm going to post what I had for today's lecture too. I'll post that everything tonight. And then I will just write down the solutions to the sample exam and I will post that separately just to make sure that you have it. Okay. I'll do all of it tonight. If not, early morning tomorrow. Yes, sir.
Have you uploaded like an updated like formula sheet yet for this exam?
I have not.
Okay.
Good question. There is no extra formula that I'm going to include there. There are just a couple of formulas that I really expect you to know them. So, for example, this last section, section 6, the only equation that we have there, and I expect you to know it, is that HF being F L over D V squared over 2G. I expect you to know this.
Yeah.
And then for F, obviously, if it's laminar, it's 64 over Reynolds number. Again, I expect you to know that. I expect you to know what is the definition of Reynolds number, which is rho v d over mu, okay, or vd over nu. So these are what we had in section 6. So that's what we had, 3 equations, and I expect you to know all 3 of them. Section 5, we don't have any equations in section 5. So it's just like pi theory that you are expected to know. Maybe the definition of Reynolds number comes from section 5, but section 4, all you have there is the continuity equation and the Navier-Stokes equations, right? Again, you're expected to know them. If you remember when I was covering Navier-Stokes equation, I told you that I am going to ask this question in the exam. Remember, I said I'm going to ask you to write down Navier-Stokes equation in one of those directions. It could be X, Y, or Z, and explain what those terms are, right? So, for example, I want you to know what that mu second derivative of u with y plus second. Well, does anyone know what this is? So, for example, if I ask you this question, do you all know what it is? Let me erase this. If I give you this, for example, mu second derivative of v with x, and then second derivative of v with y, and then second derivative of v with z. What is this? In what direction? Y direction. Yes. You see, these are the things. So I'm not going to add equations. The equations that we have, I really expect you to know, but I will add some tables. You see, I will add the information that you would need to solve the problems in terms of tables, in terms of conversions, unless it's a conversion of inch to foot. Obviously, I expect you to know that. But if it's like horsepower to pound force foot per second, I'm going to provide that. All of the fluid properties will be provided to you, like new mu, density. Give me a minute, please. All of those, I expect you, I'm going to provide them to you. Okay. One other thing that I expect you to know is curl of a vector, curl of velocity is vorticity, right? I expect you to know that. So I might give you a vorticity vector and be like, what would be the, sorry, I might give you a velocity vector and ask you to find vorticity at a certain time and certain point. You just need to find the curl of it and then plug that x, y, z, and t in that curl. You need to know curl of velocity is vorticity, right? So no new equations in the equations in the formula sheet, but yes, new tables, new data, whatever you need.
The tables directly from the PDF from section 6, like exactly as it is in there.
Yes.
Okay.
Yes.
So that
Yeah.
has some formulas like built into it.
Yeah.
So,
It's going to be exactly like those. And then if there is a question about minor losses, there will be whatever you need in order to find those resistance coefficients or loss coefficients for minor losses. Yes.
I know with the minor loss and everything, it won't be like how we kind of have with the homework where you
No,
have to do
no.
different sections.
If I give you a problem for the pipe, which obviously I will give you a pipe problem, it is not going to be multi-sections with different diameters and everything, because I still recommend you work that problem, which I'm going to post its solutions either late tonight or early tomorrow morning, because it prepares you very well. If you can do that problem, then the exam problem is going to be easier for you, hopefully. But since you don't have that much time there, it's just 1 hour, 15 minutes. I can't give you a problem that you have to do Reynolds number 3 times, 3 epsilon over d, going to the Modi chart 3 times. If you need to go to Modi chart, you will need to go to Modi chart only once in the problem that I give you. Because again, it's just 75 minutes. It's not even 75 minutes. By the time that we decide, we lose a few minutes in the beginning.
And then obviously, like at the beginning of the recitation today, like the problem you worked where it was just like a horizontal pipe and it's like a straight diameter out the whole thing. Like technically you are using the energy equation there, right? It's just everything's zero because
Yes.
it's horizontal. So do we need to write that out initially or like say like verbally that like all those things cancel out, or can we do the same thing we did?
We can do the same thing. You can do the same thing. But know that if it was not horizontal, then you better use that. Or let's say if there is a turbine, like what we talked about today, this morning at the lecture, remember that example that's made up there, and then we had a turbine, and then we found the head of that turbine. If you're dealing with a case like that, that we wrote the energy balance between point 1 and 2, point 1 and 2 being at the surface of the two reservoirs, then it's really easier for you if you write the energy equation. Otherwise, you will be confused. You know what I'm saying? Okay. There's a question online.
Hi, so you were saying that if you're gonna give one of those pipe problems, we're gonna only have to go to the Moody chart or find the Reynolds number once.
Yes,
Because like in the homework, we had to find it 3 times.
3 times. Because I
But
wanted to prepare you. Yeah. I wanted to give you something harder so you would, wrestle with it a little.
just so everyone is adequately or well prepared to perhaps handle the problem on the exam, which would have just one, where you have to find those only once.
Yes. Correct.
Mm-hmm. Yes.
Yeah. Okay. Any other questions? Yes.
Okay. Oh, exam Thursday, 11 to 12:15, like always.
Like always, same room. Yeah. And if something comes up, if you have any other questions tomorrow, you see me in my office, don't be shy. Let me know. Okay. And I won't be shy if I have to run to a meeting, but I'll let you know when you can come back. So we will figure something out. Okay. This was good, I think. So good luck with everything. And I will see you on Thursday.
Well,
I was gonna say curiosity question. So I know like clay mathematics, they say that like the Navier-Stokes is, like, doesn't technically have a solution. I was like wondering why that is, I guess, because